So in this video, we are going to cover how RAG actually works. So a language model only knows what it saw in training. So if you ask about your company handbook, last week's news, or your own code base, it either refuses or makes something up. That's what you call an hallucination. So retrieval augmented generation fixes this without retraining a single thing. The idea is simple. Find the right text first, then let the model answer from it. So over the next few minutes, we will build a RAG system end to end from raw documents to a grounded answer. And we will also look at where it actually goes wrong. So the problem is that we will start with why this is required in the first place. So a trained model has three gaps. As you know, its knowledge is frozen at a cutoff date. So it never saw anything newer after that. So whenever you ask a question after the cutoff date, it will say that, okay, I either don't have the knowledge or it will make something up for sure. So it never saw your private data at all, like your tickets, your documentations, your database, nothing. And when it does not know, it often answers anyway, and like it will answer fluent and wrong. So you could retrain the whole model on your data, but that is slow and very expensive and out of the date the moment a document changes. So RAG takes the opposite approach. Leave the model alone, and at question time, hand it the exact passages it needs. The model stops recalling from memory and starts reading from a source you control. So the heart of retrieval is search that understands meaning, not just keywords. Keyword search fails when the question and the answer use different words. Someone asks how to reset a password, but the document actually says credential recovery. Both of them are different things. So embeddings is the answer for this. So an embedding model turns any piece of text into a single vector or multiple vectors, a long list of numbers that captures the exact meaning of it. So texts about the same idea land close together in that space, even with no shared words. So instead of matching letters, you match positions. So reset passwords sits near credential recovery because they mean the same thing. So this is the same vector idea behind language models, now pointed at search. You cannot embed a whole book as one vector and expect good results. Too much meaning gets averaged into a single point and the details obviously blurs. You will get a gray line in between. So you split these documents into chunks, usually a few hundred tokens each. You have to figure out which works best for you. Like maybe it can be 200 tokens, maybe it can be 500 tokens. So chunk too large and retrieval pulls in noise around the answer. And if you chunk too small and you cut the idea in half, losing the context that made it make sense. Good chunking respects structure, splitting on paragraphs, headings, or sections rather than every fixed number of characters. A common trick is overlap, letting each chunk share a little text with the next one, so a sentence on a boundary is never orphaned. Chunking is unglamorous, but it quietly decides how good your whole system feels. Now, embed every chunk and store the vector somewhere you can search fast. So that is what you call a vector database. So in vector database, what happens is that at query time, you embed the question as well, and then look for the stored vectors nearest to it. So nearness is usually a cosine similarity, the angle between two vectors, which measures how aligned their meanings are. Checking every vector one by one works for a few thousand chunks, but not for millions. So scaling in this particular format, it doesn't happen. So vector databases use approximate nearest neighbor search with index structures like HNSW that build a navigable graph of vectors. So you try a tiny bit of accuracy for an enormous speedup, finding the closest matches in milliseconds across huge collections. So now with the index built, retrieval is the easiest part. So we will take the user's question, embed it, and ask the database for the top k nearest chunks. So it's going to be often the closest 3 to 10. These come back ranked by similarity. So here is a detail that matters in production. So pure vector search can miss exact terms, such as let's take an example of product code or an error number, because meaning doesn't always means the exact string matches. So in this particular case, most of the time strong systems run hybrid search, combining vector similarity with old-fashioned keyword matching. So now we have a blended two ranking scenario. You get the best of both semantic recall and the exact precision. The output of this stage is a small pile of passages that should contain the answer. Now this is the generation step where the G in RAG comes in. You build a prompt that places the retrieved chunks in front of the model with an instruction saying like answer using only the context below, and if it's not there, say you do not know it. So then you add the user's exact question. So the model now has a ground facts within its context window and writes an answer which is grounded in them. A good prompt also should ask for citations, so the model points back to which chunk each claim came from, so that as an audit purpose for future debugging we can use that. That single instruction, answer only from the context, is what turns a confident guesser into a system you can trust, because every claim is traceable to a source you provided. But there is a weak link in all of this. The fast vector search is good at recall but rough at ranking. So the single best passage might come back fourth, not first. Reranking fixes this order issue. So what you do is, after retrieval, you pass each candidate chunk and the question together through a cross encoder, a smaller model that reads both at once and scores its true relevance. It is too slow to run over your whole database, but perfect for resorting a short list of, let's say, 20 down to the best number of 3 of them. The pattern is retrieve wide, then re-rank narrow. So cast a broad net cheaply, then spend a little more to put the genuinely best passages at the top, which where the model pays them the most attention, obviously. So RAG is not always magic, and it fails in specific ways which should be worth knowing. So if you are implementing RAG in production, let's say if one retrieval misses, the model never sees the answer and falls back to guessing. So a retrieval bug looks like a hallucination. So if your chunks are poor, the right facts are split or buried, and no prompt can actually save them. So models also suffer from lost in the middle issue, paying less attention to text stuck in the center for a long context. So passage order matters as well. Let's say even if you have a perfect context, a model can still ignore it and answer from memory, which is why the answer only from context instruction is not optional. Most RAG problems are not generation problems, they are retrieval and data problems wearing a generation mask. So if you cannot measure it, you cannot improve all these issues, right? So, and in case of RAG, you cannot eyeball your way through thousands of questions for sure. So you evaluate the two halves separately. Let's say for retrieval, you build a set of questions with the chunks that truly answer them, then measure whether retrieval surface those chunks using recall and a rank away score like mean reciprocal rank. For generation, measure faithfulness, whether each claim in the answer is actually supported by the retrieved text, and relevance, whether it actually addressed the question itself. A common shortcut is to use a strong model as a judge, scoring answers against the sources automatically. So once these numbers exist, every change, a new chunk size, a re-ranker, a different embedding model becomes a measurable experiment instead of a guess. So that is RAG end to end. Split your documents into chunks, embed them into vectors, and store them in an index you can search fast. At question time, embed the query, retrieve the nearest chunks, and re-rank them to the best few. Drop those into the prompt with an instruction to answer only from the context, and the model writes a grounded, citable answer, which is always good for us. Watch for the failure modes, retrieval misses, and weak chunks, and measure both stages so you can improve them. No retraining, no frozen knowledge. Just the right amount of text found at the right moment, handed to a model that knows how to read. So if you have any question, let me know in the comments.